We have a bit of a problem. You see, when we look at the world around us at tables, chairs, and baseballs, we think we know what's going on. We have this set of ideas called common sense. If I throw a ball, you know exactly where it's going to go. It follows a nice, smooth path. It has a position and it has a speed. And this is the world of the giants. We are the giants. We are huge, lumbering things made of trillions upon trillions atoms. And because we are so big, we see a world that looks very tidy and predictable. We call this classical physics. It's the physics of Isaac Newton. And for a long time we thought it was the whole story. It felt right. It felt solid. But then we started to look closer. I mean really close. We started looking at the tiny bits that make up the world, the atoms, the electrons, the photons of light. And what we found there didn't just surprise us. It made our common sense look like a total disaster. Down there in the world of the very small, things don't behave like baseballs. They don't have nice, tidy paths. They don't stay in one place. In fact, if you try to use your everyday intuition to understand an electron, you will get nowhere. You'll get confused, and you might even get angry. But the universe doesn't care if you're angry. It just keeps doing what it's doing. So my goal today is not to tell you that the world makes sense in the way you want it to. My goal is to show you how the world actually works, even if it sounds impossible. We aren't going to use big, scary words if we can help it. We are going to look at nature's real rules, the ones she uses when we aren't looking. Let's start with an experiment. This is the heart of the whole thing. If you can understand this, you understand the core mystery of quantum mechanics. Imagine we have a wall with two small holes in it, two slits. Behind the wall, we have a screen that can record whenever something hits it. Now imagine we are firing something simple at these holes. Let's say we're firing little balls of mud. If a ball of mud goes through the left hole, it hits the screen and leaves a mark. If it goes through the right hole, it leaves a mark there. After a while, you'd see two big piles of mud marks on the screen right behind the holes. That makes sense. That's what things do. Now let's try it with waves. Imagine this whole setup is underwater. We send a wave toward the two holes. The wave hits the wall and ripples through both holes at the same time. On the other side, the two new ripples start to overlap. In some places, the peak of one ripple meets the peak of another, and they make a bigger wave. In other places, a peak meets a trough, and they cancel each other out. They flatline. When the waves finally hit the screen, you don't get two piles. You get a pattern. You get a series of stripes, places where the waves were strong, and places where there was nothing at all. We call this an interference pattern. It's what waves do. Now comes the impossible part. We do the same thing with electrons. Now, for a long time, people thought electrons were like the little balls of mud, just tiny solid bits of matter. So we fire them one by one. We fire one electron, it hits the screen. Click. We fire another. Click. We do this for a long time. If electrons were like mud, we should see two piles. But we don't, even though we fired them one at a time, so they couldn't possibly bump into each other. They slowly form the stripes. They form the wave pattern. This is where your brain should start to itch. How can a single solid electron fired all by itself know about both holes? To make those stripes, something has to go through both holes and interfere with itself. Does the electron split in half? No. We've checked. It always arrives as one whole click. Does it take some weird curvy part? Well, here's the kicker. If we put a little light or a detector next to the holes to see which hole the electron actually goes through, the stripes disappear. The moment we watch it, the electron starts behaving like a ball of mud again. It goes through one hole or the other, and we get the two piles. But if we stop watching, it goes back to making stripes. The conclusion is inescapable. Even if it's hard to swallow, we have to stop thinking of the electron as a thing that takes apart. In the quantum world, an electron isn't at point A or point B. It's in a state of, well, we don't have a good word for it in English. It's a state of possibilities. When we aren't looking, it explores all the options. It's only when we force it to show its face, when we measure it, that it picks a spot. Nature is not made of objects in the way we think. It's made of something else. So if we can't say where the electron is, how do we do physics? We can't just give up and say it's magic. We need a way to calculate what's going to happen. And this is where we have to change how we count. In the classical world, if you want to know the chance of something happening, you just add the object. If there's a 10% chance it goes through hole A and a 10% chance it goes through hole B, then there's a 20% chance it gets to the screen. Simple. But in the quantum world, that simple math fails. It gives the wrong answer. To get the right answer, we have to use a new trick. I like to think of it as a little stopwatch. Imagine that every particle has a tiny invisible stopwatch inside it. As the particle moves through space, the hand on that stopwatch is spinning around and around. Now, instead of asking what is the probability of the electron hitting the screen, we ask for something called a probability amplitude. That's just a fancy name for an arrow. Imagine the electron wants to get from the source to a specific spot on the screen. It can go through hole A. For that path, we look at the stopwatch when the electron arrives and draw an arrow pointing in the same direction as the stopwatch hand. Let's say it's pointing up. Then we look at the path through hole B. The distance might be slightly different, so the stopwatch hand might have spun a bit more. For that path, the arrow might be pointing down. Now here is the secret rule of the universe. We don't add the probabilities, we add the arrows. We put them tip to tail. If one arrow points up and the other points down, they cancel each other out. The total arrow is 0. And what does a zero-length arrow mean? It means the probability is 0. The electron never hits that spot. That's why we get those empty stripes in the pattern. If the two arrows point in the same direction, they add up to a long arrow, which means a very high probability. This is how nature keeps her books. She doesn't keep track of where things are. She keeps track of these little spinning arrows, these amplitudes. And to find out what happens in the real world, we just add up all the arrows for all the ways an event could happen. Once we have the final total arrow, we measure how long it is and square that length. That number, the square of the arrow, is the probability we see in our experiments. You might say, that's just a trick, that's just math. It doesn't tell me what the electron is really doing. But that's the point. This math is the only thing that actually matches what we see in the laboratory. The idea that an electron is a little ball is the myth. The spinning arrow is much closer to the truth. We have to learn to trust the rules of the game, even when they seem to break the rules of our own daily lives. This brings us to a very deep realization. If we have to add up arrows for different paths, we start to see that the whole idea of a single path is a bit of a dream. Why stop at 2 holes? What if there were 3, or 10, or 1,000,000? What if there were no holes at all, and the electron was just moving through empty space? Well, if there are no walls in the way, the electron has an infinite number of ways to get from here to there. It could go in a straight line, it could go in a zigzag. It could go up to the ceiling, dance around a bit, and then come back down to the screen. And according to the rules of quantum mechanics, we have to account for all of them. We have to draw an arrow for every single possible path, no matter how crazy it seems, and add them all together. Now this sounds like a nightmare. How could you ever add up an infinite number of arrows? This is where the advanced calculus comes in, but don't let the name scare you. Calculus is just a tool for adding up lots of tiny things. In this case, we are adding up tiny arrows. When you do the math, when you add up all the crazy curvy paths, something beautiful happens. For most of the wild paths, the arrows point in every which way. There are many points left, the next point's right, the next point's up. They all cancel out to nothing. But for the paths that are very close to a straight line, the arrows all point in almost the exact same direction. They don't cancel, they reinforce each other. They build up into one big strong arrow. This is why when you throw a baseball, it looks like it's taking one single straight path. It's not because it is a single object on a single path. It's because all the other quantum possibilities have cancelled each other out, leaving only the classical path. The common sense world we live in is just the sum of all the impossible paths of the tiny world. So you see, quantum physics doesn't say that the world is chaotic. It says the world is far more interconnected than we thought. Every event is the result of a vast, invisible collection of possibilities all merging together. We are like people looking at a giant tapestry from a mile away. We see a simple solid shape. But when we get up close, when we look at the atoms, we see that the shape is made of millions of tiny threads, all woven together in a way that we never could have had. I want you to think about that for a moment. This isn't just a story. We've tested this. We've tested it with light, with atoms, and with even bigger molecules. It always works. We can predict the behavior of light hitting a mirror, or the way an atom holds onto its electrons with more precision than almost any other theory in human history. We do it by using these spinning arrows and adding up the possibilities. It requires a change in how we think about reality. We usually think reality is what we see, But in physics, we've learned that what we see is often just a very blurry version of what is actually happening. The real world is a world of amplitudes. It's a world where things don't have a location until they are forced to. It's a world where a single particle is, in some sense, everywhere at once until we pin it down. If this makes you feel a little dizzy, that's good. It means you're paying attention. Even the people who spent their whole lives studying this, the ones who won the big prizes, they felt dizzy too. The difference is that they learned to enjoy the dizziness. They realized that nature is much more imaginative than we are. She found a way to build a solid, predictable world out of a foundation of shifting, dancing possibilities. In our big world, we have rules like energy must be conserved, and nothing goes faster than light. And those rules are true for us. But they are true because of the way all those tiny arrows add up. If you change the scale, if you look at a single electron for a fraction of a second, you might see it borrow some energy, or take a path that seems to defy the speed limit. But it has to pay it back, so quickly that we giants never notice. The universe has a very strict accounting system. This is the beauty of the Feynman way of looking at things. If I can call it that, it's not about memorizing equations. It's about visualizing the process. It's about seeing the little arrows. It's about understanding that the math is just a way to keep track of the spinning. Whether you're talking about light or gravity or the way magnets work, it all comes back to this same fundamental dance. Let's take another example. Think about how light reflects off a mirror. We were taught in school that the angle of incidence equals the angle of reflection. Light hits the middle of the mirror and bounces off. But that's the giant view. If we use our quantum rules, we say that the light actually hits every part of the mirror. It hits the left edge, the right edge, the top and the bottom. For every spot it hits, we draw an arrow. If we look at the arrows for the light hitting the edges, we find they arrive at different times. So the arrows point in different directions. They cancel out. But for the light hitting the middle, the paths are almost the same length. The arrows arrive pointing the same way. They add up. So even though the light hit the whole mirror, we only see the reflection in the middle. The law of reflection is just the result of a bunch of arrows not cancelling each other out. This is what I want you to take away from this first look at the quantum world. Don't worry about how it can be that way. Don't ask, but what is it really doing? Because nobody knows the answer to that. All we know are the rules of the game, and the rules say, add up the arrows. If you follow that one simple instruction, you can understand how light works, how atoms stay together, and why the world looks the way it does. Nature has a logic, but it's not our logic. It's a logic of probability, of interference, and of infinite path. It sounds impossible, but only because we are so big, and the world is so small. Once you step down into that tiny realm and leave your common sense at the door, you'll find a world that is more strange, more beautiful, and more precisely balanced than anything we could have invented. It's a world where the impossible happens every single day, trillions of times a second, right under our noses. And all we had to do to see it was look a little closer and learn how to act. I'll leave you with this thought. The next time you look at a rainbow or a reflection in a window, don't just see the colors. Think about the trillions of tiny stopwatches spinning away and all the paths that didn't happen so that the one you see could exist. That is the real world. That is the quantum world, and it's waiting for us to figure out the rest of the rules. For now, we've got a good start. We've got our arrows, and we've got our math. And as it turns out, that's enough to begin to see the true face of the universe. Now, if you're still with me, you've realized that the world is a lot more crowded than it looks. We've talked about how a single electron or a single photon doesn't just take one path, it takes them all. It's like a giant cosmic audit, where every possible way of doing something has to be accounted for with a little spinning arrow. But you might be wondering, if everything is so busy taking every path at once, why does the world look so solid? Why don't I see my coffee cup taking a detour through the moon on its way to my mouth? This is a fair question. The answer takes us into the heart of what we call quantum electrodynamics, or QED for short. Don't let the name scare you. Just a fancy way of saying the way light and matter interact. And believe it or not, almost everything you see, the color of your shirt, the way your hand doesn't pass through the table, the very fact that atoms exist, is all down to just 3 basic actions. Think about that. The entire universe, in all its complexity, is built out of a very simple set of rules. It's like a game of chess. The rules are simple, but the games you can play are infinite. In the quantum world, the three main moves are these. A photon goes from one place to another, an electron goes from one place to another, and an electron emits or absorbs a photon. That's it. That's the whole show. Everything else is just a combination of these three things happening over and over again. But because these things happen according to the rule of the spinning arrows, the results are spectacular. Let's look at that third move, the one where an electron and a photon meet. We call this a coupling. When an electron moves along, it has a certain chance of spitting out a photon. Or if a photon is passing by, the electron has a certain chance of gobbling it up. Now, how do we represent the chance of this happening? You guessed it, with another arrow. But this arrow is special. It has a very specific length. In fact, the length of the arrow for an electron to emit or absorb a light particle is about 0, 1, or 1. We call it the fine structure constant. It's a number that nature just picked, and we have no idea why. If it were even slightly different, the stars wouldn't shine, and you wouldn't be here to listen to me. But here is where the advanced calculus, the adding up, gets really interesting. Imagine two electrons heading toward each other. In the old giant-size physics, we'd say they repel each other because they have the same charge. They push apart like two magnets. But in the tiny world, what's actually happening? The first electron spits out a photon, and the second electron catches it. It's like two people on ice skates throwing a heavy medicine ball back and forth. Every time they throw or catch the ball, they get pushed apart. That push is what we feel as an electric force. But wait. According to our rules, we have to consider every way this could happen. Maybe they exchange one photon. Maybe they exchange two. Maybe one electron spits out a photon. That photon turns into an electron and a positron, a sort of mirror image electron. For a split second, they vanish back into a photon, and then the other electron catches it. This sounds like science fiction, but it's just the way the arrows work. We have to draw a diagram for every one of these possibilities. I like to use little drawings with squiggly lines for light and straight lines for electrons. These little pictures help us keep track of the arrows we need to add up. Now, as you add more squiggles and more loops, more complications, the arrows get shorter and shorter because you keep multiplying by that Luro 1 chance number. The more complicated the path, the less it contributes to the final result. This is why the world doesn't look like total chaos. The simplest paths usually carry the most weight. However, if you want to be really precise, if you want to know the answer to 10 decimal places, you have to sit down and do the hard work of adding up the arrows for the crazy paths too. When we do this, the results are incredible. We can calculate the magnetic strength of an electron, and when we go into the lab to measure it, the math and the reality match up perfectly. It's the most accurate prediction in the history of human thought. It's like predicting the distance from the Earth to the Moon within the width of a single hair. This tells us something profound. It tells us that our crazy idea of adding up every possible history is actually how the world works. Nature isn't calculating anything, of course. She's just being herself, but the way she is can be described by this beautiful complex sum of paths. This brings us back to the question of why things feel solid. Why don't you fall through the floor? It's because the electrons in your shoes and the electrons in the floor are constantly exchanging virtual photons. They are talking to each other using the rules of QED. The arrows for those electrons passing through each other cancel out so perfectly that it feels like a solid wall. Solidity is just a massive coordinated cancellation of quantum possibilities. Let's think about atoms for a second. We often see pictures of atoms that look like little solar systems, with electrons orbiting a nucleus like planets. But that's a lie. If an electron were just a little planet orbiting a nucleus, it would be constantly changing direction. And in our rules, when an electron changes direction, it should spit out a photon. If it did that, it would lose energy and spiral into the center in a tiny fraction of a second. The atom would collapse. The fact that you are sitting here proves that the solar system model is wrong. So what is the electron doing? It's doing its every path dance. It's spread out in a cloud of probability. It exists in a state where the arrows for it being at different distances from the center all balance out. It finds a stable pattern where the stopwatch hands all line up in a way that keeps the electron from falling in. This is why atoms have specific sizes. They aren't held up by little struts or solid walls. They are held up by the requirements of the math, by the way the arrows have to add up. Now I want to address something that bothers people. They say this is all very well for electrons and light, but what about me? I have a soul, I have thoughts, I have a life. Well, from a physicist's point of view, you are a very, very large collection of these interactions. Your brain is a forest of electrical signals, which are just electrons moving and photons being exchanged. Your muscles move because of chemical bonds, which are just electrons finding stable patterns between atoms. Everything you experience is built on this foundation of impossible quantum rules. Does that make life less special? I don't think so. I think it makes it much more amazing. Think about the complexity required to take these simple rules. An electron goes here, a photon goes there, and build a human being who can think about the universe. It's like taking a few simple notes and composing a symphony that lasts for 100 years. The calculus of life is just the adding up of trillions of these tiny quantum arrows until they form something large enough to have a name. The most important thing I can teach you is not to be afraid of the strangeness. Many people try to explain quantum physics by saying it's mystical or that mind creates reality. I don't think that's very helpful. It's much more exciting to see it as a set of mechanical rules that just happen to be different from the rules we are used to. It's not magic. It's just how the gears of the universe turn when you get down to the smallest scale. If you want to understand the world, you have to be willing to accept it as it is, not as you want it to be. If nature wants to use spinning arrows and some over-histories to run the show, then that's what we have to learn. And the wonderful thing is that we can learn it. We've found the tools. We've found that even though we are giants, we can use our giant brains to figure out the rules of them. We can use calculus to bridge the gap between the common sense of a baseball and the impossible dance of an electron. As we look forward, we see that these same rules apply to everything. We've used them to understand the heart of the sun, the birth of stars, and the way light travels across the vacuum of space. We are even trying to use them to understand gravity, though that's a much tougher nut to. But the lesson remains the same. The universe is a consistent logical place. It's just that its logic is much deeper and more imaginative than the logic we use to cross the street or catch a ball. So the next time you look at a light bulb or look in a mirror or just feel the weight of your body on a chair, remember the dance. Remember that beneath the surface of everything you see, there is a frantic, beautiful, and incredibly precise counting of possibilities going on. There are trillions of tiny stopwatches spinning, arrows being added tip to tail, and a grand invisible calculus that holds everything together. It's a world where nothing is certain, yet everything is precisely accounted for. It's a world where the paths not taken are just as important as the path you see, and most of all, it's a world that we are finally beginning to understand, one arrow at a time. It's not crazy, it's just the truth. And the truth is always more interesting than anything we could have made up. We just had to be brave enough to look at the small stuff and follow the math wherever it led. And it led us here, to a universe that is far more wonderful than we ever imagined.